Hi, I'm Neil deGrasse, and today I'm going to tell you 100 amazing facts about exoplanets and super Earth that you don't know. Subscribe, and let's get started. Number one, the meaning of the term exoplanet. The term exoplanet comes from extra or outside of and planet. This refers to any planet that orbits a star outside the solar system. Number two, what must a planet do to be an exoplanet? An exoplanet is usually defined by three simple rules. First, it's lightweight. Its mass is below about 13 times Jupiter's. Second, it orbits something like a normal star, a brown dwarf, or a stellar remnant, such as a white dwarf. Third, it must be much less massive than what it orbits, so it's clearly a planet, not a near equal mass partner in a double system. Number three, can there be more planets than stars in the galaxy? Astronomers have found that there may be more planets than stars in the Milky Way. Studies with the Kepler and Spitzer telescopes estimate that most stars have at least one planet, since our galaxy contains about 100 to 400 billion stars. The number of planets could easily exceed that figure. This suggests that planets are common and not exceptional in the universe. Number four, the current exoplanet number. As of Monday, September 22nd, 2025, astronomers had 6,007 confirmed exoplanets on the books. That running total is tracked by NASA's Exoplanet Archive, which adds new worlds as they're verified by the research community. Number five, exoplanets are named with the letter B. Exoplanets are named following the convention of adding a lowercase letter to the name of the host star. The first letter used is B because the A is reserved for the star itself. Thus, the first planet discovered in a system receives the letter B, the second C, and so on. For example, the first exoplanet of 51 Pegasi is called 51 Pegasi b. This naming system is accepted by the International Astronomical Union. Number six, the first exoplanet discovered. In 1992, astronomers Alexander Wolszczan and Dale Frail made the first confirmed discovery of planets beyond our solar system, three worlds circling a pulsar called Pi Esser b 1257 plus 12, about 2,300 light years away. A pulsar is the ultra-dense core left after a massive star explodes. It spins fast and sweeps space with radio beams like a lighthouse. Finding planets in that harsh environment was a shock. Nobody expected worlds to survive around a dead star. That surprise kicked off the modern era of exoplanet science. Number seven, what was the first direct image of an exoplanet? The first exoplanet to be directly imaged is called 2M 1207b. Captured by the European Southern Observatory's Very Large Telescope in 2004, it is a planet of giant mass, about 5 times that of Jupiter, orbiting a brown dwarf called 2M 1207, and was discovered thanks to infrared images using adaptive optics. Number 8, the color and brightness of exoplanets. A planet's look depends on three things: how far it is from its star, how much light it reflects or albedo, and how much light it receives. Clouds and hazes can make a world bright and pale, while clear, sooty, or metal-rich skies make it dark. Tres 2b is the darkest known, a hot Jupiter that reflects under 1% of starlight, darker than coal. By contrast, some cloudy giants can look bright. Others, like HD 189733b, appear deep blue because tiny particles scatter blue light. Number 9, synonym of exoplanet. Today, most people say exoplanet, but you'll also see extrasolar planets. They mean the same thing. A planet that orbits a star outside our solar system. Exoplanet is just the shorter, more popular term. Extrasolar is the older, more formal way to say it. Number 10, there are 4 types of exoplanets. Astronomers often group exoplanets into 4 handy categories: rocky worlds like Earth, small solid surfaces, super Earths, which are bigger than Earth but still mostly rock and metal, mini Neptunes, a middle class with rocky cores wrapped in puffy, hydrogen-rich atmospheres, and gas giants like Jupiter, huge planets made mostly of hydrogen and helium. Number 11, the first one around a sun-like star was found in 1995. In 1995, Michel Mayor and Didier Queloz found the first planet orbiting a sun-like star, 51 Pegasi b, a hot Jupiter, a gas giant parked absurdly close to its star, only 0.05 IU away. It whips around in about 4 days, far faster and nearer than Mercury is to our sun. The discovery was so transformative that the pair received the 2019 Nobel Prize in Physics. Number 12, 2 types of ways to find exoplanets: indirect and direct. The indirect methods, which watch the star to reveal a hidden planet. Here there is the transit method and the radial velocity method. These tools are powerful and work for many worlds, but we don't actually see the planet itself. The direct method tries to photograph the planet by blocking the star's glare with special optics. In short, indirect methods find lots of planets by reading the star. Direct imaging is rarer, but it lets us see the planet. Number 13, the most commonly used methods to detect exoplanets. According to NASA and ISI, the two workhorse techniques for finding exoplanets are transits and radial velocity. In transit, a planet slips in front of its star and causes a tiny, regular dip in starlight, like a moth briefly dimming a porch light, letting us estimate the planet's size. Radial velocity tracks the star's subtle wobble as the planet's gravity tugs it toward and away from us, shifting its spectrum and revealing the planet's mass. Used together, these methods have confirmed thousands of worlds beyond our solar system and even let us infer their density, whether they're rocky, puffy, or something in between. Number 14, what is the transit method precisely? It is a technique used to detect exoplanets by measuring the decrease in light from a star when a planet passes in front of it. This transit causes a small periodic dimming that astronomers record on a light curve. By analyzing these variations, the size of the planet and its orbit can be calculated. It has been the most successful method, allowing thousands of worlds outside the solar system to be discovered. Number 15, and what is the radial velocity method? The radial velocity method finds exoplanets by watching a star's tiny wobble, a tug of war caused by an unseen planet. As the star moves toward us, its spectral lines shift slightly bluer. As it moves away, they shift redder, known as the Doppler effect. By tracking this back and forth pattern, astronomers can pin down the planet's orbital period and estimate its mass. Paired with the transit method, which gives the planet's size, radial velocity helps reveal a world's true mass and density. Number 16, another method, the gravitational microlens. It is a method that allows us to discover planets that are very far away, even thousands of light years away. It works when the gravity of a star, with or without a planet, acts as a lens, amplifying the light of another, more distant star. If a planet accompanies the lensing star, an additional signature is produced in the observed brightness. This technique is very sensitive to distant and low-mass planets, which could not be detected with other methods. Number 17, finding planets by a star's tiny sidestep. Astrometry finds exoplanets by checking if a star shifts a tiny bit in the sky. A wobble caused by an unseen planet tugging on it. In 2020, astronomers did this with radio telescopes linked across the IUS from Hawaii to Puerto Rico. They spotted an ultra-cool dwarf star making that small sidestep and worked out that a Saturn-sized planet is pulling on it, taking about 221 days to go once around its star. Number 18, a super-Earth, a type of exoplanet. A super-Earth is a type of exoplanet whose mass is greater than that of Earth, but much less than that of giants such as Neptune or Uranus. Generally, its mass is between 1 and 10 times that of Earth. They are not necessarily habitable or similar to our planet. Some may be rocky, others with dense atmospheres or extreme temperatures. The term describes size and mass, not living conditions. These worlds are common in the galaxy, although they do not exist in our solar system. Number 19, another type, the mini-Neptune. A mini-Neptune is an exoplanet smaller than Neptune, but with a dense, gas-rich atmosphere. They usually have radii between 2 and 4 times that of Earth and masses intermediate between super-Earths and ice giants. Many are thought to possess rocky cores covered by thick envelopes of hydrogen and helium. They are not direct analogs of any planet in our solar system. Number 20, exoplanets, hot Jupiters, orbit very close to their star. Hot Jupiters are giant gaseous exoplanets that orbit very close to their star, much closer than Jupiter in our solar system. Their extreme proximity generates high temperatures, which causes some to have inflated atmospheres. These planets have very short orbital periods, some as short as 2 or 3 days. Their most outstanding feature is the fast orbit due to their proximity to the star, which makes them easy to detect due to their transit or radial velocity effects. Number 21, rogue planets are a type of exoplanets. An exoplanet is any planet beyond our solar system, but not all have suns. Some are free-floating rogue planets, drifting through the galaxy in perpetual night. We spot them via gravitational microlensing. When their gravity briefly magnifies a distant star, rogues can be ejected from young solar systems after chaotic gravitational shoves. Others may form in isolation, like undersized failed stars that never ignite fusion. Their existence proves planets don't need a star. Some simply wander the Milky Way on their own. Number 22, exoplanets are used to find exomoons. An exomoon is a natural moon that orbits an exoplanet. Exoplanets help us search for these moons because when a planet passes in front of its star, The moon might leave tiny extra clues in the starlight, like a small extra dip or slight changes in the timing and length of the transit. But exomoons are very hard to detect. They're small, faint, and extremely far away. So far, astronomers have found a few promising candidates, but there is no widely confirmed exomoon yet. Number 23, there are some exoplanets orbiting two suns. They're called circumbinary planets, and the first confirmed one, Kepler-16b, instantly evoked Star Wars Tatooine with its double sunsets. A circumbinary planet doesn't loop around each star separately. It orbits both stars at once, specifically the pair's common center of mass, or barycenter. For the orbit to be stable, the planet usually sits several times farther out than the distance between the two stars. Too close and the stars' tug of war would fling it away. Number 24, other exoplanets orbit in more than two stars. Some planets live in systems with 3 or even 4 suns. The stars form a tight pair in the middle, and any other stars stay much farther away. A planet can orbit safely if it circles well outside that inner pair, or if it stays close to just one star while the others are far off. The big idea is spacing. Wide gaps keep the pulls of gravity from turning chaotic. Kepler-64b is a good example in a 4-star family. With the spacing right, these orbits can stay stable for a very long time. Number 25, exoplanets with unusual orbits. Not all exoplanets travel in neat circles. Some follow highly stretched eccentric paths that send them looping far from their star and then diving back in for a scorching close pass. These wild tracks often come from gravitational run-ins with other planets or a distant companion star, which can yank an orbit out of shape. Number 26, the planet with an unusual orbit. A great example is Eichdai 80606b. It spends most of its 111-day year far from its star, then swings in very close on a brief, fiery flyby. As it rushes past, the planet's atmosphere heats up by hundreds of degrees in hours, then cools again as it heads back out like a cosmic slingshot ride. These extreme orbits make for dramatic seasons and fast-changing weather you'd never see in our own solar system. Number 27, do some exoplanets orbit in opposite directions? Yes. A retrograde orbit is when a planet circles its star opposite to the star's spin. We catch this using the Rossiter-McLaughlin effect during a transit. As the planet crosses the star's face, it first hides the side rotating toward us, light skews slightly bluer, then the side rotating away, redder. The pattern of that spectral bump reveals whether the planet's path is aligned, tilted, or reversed. Number 28, some exoplanets rotate so fast that their shape is flattened. If a planet rotates too fast, the centrifugal force at the equator pushes outward more than at the poles, making it an oblate spheroid flattened at the poles. This happens most easily to gas giants, whose interiors can shift and flow. How do we tell from far away? By watching very precise transit light curves. During the first and last moments of a transit, a slightly squashed planet blocks starlight in a subtly different way than a round one. Those tiny shape clues let astronomers estimate how fast the planet spins and how puffy it is. Number 29, some exoplanets are darker than carbon. Yes, some worlds reflect almost no light. The champion is TRES-2b, a hot Jupiter that absorbs about 99% of the starlight that hits it, reflecting only 1 to 2.5%. For comparison, the moon reflects roughly 12%. Why is it so dark? Its super hot atmosphere likely lacks bright reflective clouds and may contain light-absorbing chemicals that soak up glow instead of bouncing it back. The result, a planet blacker than coal, barely visible next to its star. Number 30, some exoplanets are even brighter than Venus. Meet LT-TI 9779b, an ultra-hot Neptune found in 2020. It's so reflective it bounces back up to about 80% of the starlight that hits it, comparable to Venus, the brightest planet in our sky. The planet is roughly 5 times Earth's size and whips around its star in just 19 hours, so its day side gets extreme heat, around 2,000 to 3,600 Fahrenheit degrees. Yet it doesn't just glow dark red, its metal-rich clouds act like a mirror, reflecting huge amounts of light and helping the atmosphere survive so close to the star. Number 31, the Kepler telescope for exoplanets. The Kepler telescope was launched by NASA in 2009 with the aim of discovering exoplanets, that is, planets outside our solar system. Their main detection method was transit, which measures the fall of light when a planet passes in front of its star. During its 9-year mission, Kepler discovered more than 2,600 confirmed exoplanets and helped identify thousands more. Number 32, How many worlds did Kepler discover? The Kepler Space Telescope discovered a total of 2681 confirmed exoplanets during its 9-year mission. In addition, it identified nearly 3,000 additional candidates that could be planets. Its precision made it possible to detect small worlds, even the size of Earth. Number 33, TIS's searches for exoplanets in nearby stars. TIS's is a space telescope that since 2018 has been dedicated to searching for exoplanets around relatively nearby and luminous stars. Because these allow more precise measurements. It also uses the transit method to detect tiny dips in stellar brightness when a planet passes in front of its star. By focusing on nearby stars, the planets found can be better studied, for example, by analyzing their atmospheres. Number 34, confirming an exoplanet takes a lot of work, often around 1,000 person-hours from a team. First, astronomers look for repeated transits. The star must dim by the same amount for the same length of time and on a regular schedule. Then they run checks to rule out false positives like star spots or an unseen eclipsing binary using radial velocity measurements, high-resolution images of the star, and more transit data. Only after those tests agree do they stamp it as a confirmed exoplanet. Number 35, now it's easier to detect them. Before exoplanets were found, our tools could only measure a star's motion to about 1 kilometer per second. Far too coarse to see the tiny wobble a planet causes. Today's ultra-precise spectrographs can detect changes down to centimeters per second. That jump in precision turned faint, planet-made tugs into clear signals for detecting exoplanets. Number 36. Why photos of exoplanets are so rare. Taking an actual picture of an exoplanet is hard because the planet is faint and sits right next to a blinding star. To see it, astronomers block the starlight with coronagraphs and sharpen the view with adaptive optics. Even then, we usually only image big, young, hot planets that glow in infrared and orbit far from their stars, like the famous systems Icar 8799 and Beta Pictoris b. Number 37. Super-Earths are the most common type of exoplanet. Super-Earths, defined as planets with a mass greater than Earth but less than that of Neptune, appear very frequently in exoplanet catalogs. Statistical studies based on missions such as Kepler show that about 1/3 of discovered exoplanets fall into this category. This makes them the most abundant type of planet, rather than easily detectable gas giants or very small planets. Number 38, exoplanets around dead stars. A few exoplanets actually orbit pulsars, the ultra-dense, fast-spinning neutron stars left after a supernova. Pulsars sweep space with radio ticks as regular as a clock. If a planet tugs on the pulsar, those ticks arrive a tiny bit early or late, revealing the planet through timing changes. They are bathed in intense radiation around a star that literally died. These systems give astronomers a unique lab for studying how planets can survive or reform after stellar explosions. Number 39. Most exoplanets orbit red dwarfs, this type of star. Red dwarfs make up about 80% of the stars in the Milky Way, being much more abundant than stars such as the Sun because they are smaller and less luminous. It is easier to detect exoplanets orbiting close to them using methods such as transit or radial velocity. It is estimated that about 40% of these stars have super-Earths in the habitable zone, which implies that there are many worlds around them. Number 40. Why red dwarf exoplanets matter. Most stars in our galaxy are red dwarfs, small, cool, and long-lived, so they offer lots of chances for planets. Their habitable zone sits very close in, which makes planets there easier to detect. Transits happen often and the star's wobble is stronger. But there's a twist. Many red dwarfs are flare-active, blasting planets with radiation, and close worlds can become tidally locked. That mix, plenty of targets, easy signals, and real habitability challenges, makes red dwarf systems prime places to search for nearby, potentially life-friendly worlds. Number 41, day forever on one side, night forever on the other. Many close-in exoplanets are tidally locked. That means the same face always points at the star, like the moon always shows one face to Earth. The day side gets constant heating, blistering hot, while the night side sits in permanent darkness, freezing cold. Powerful winds can rush heat from day to night, and some worlds may even have clouds piled up at the terminator. The thin line between light and dark. Number 42. Astronomers have directly imaged fewer than 100 exoplanets. Taking a picture is hard because a planet is faint and sits right next to a blinding star. Number 43. Exoplanets can be in habitable zones or outside of them. Exoplanets can be found both in the habitable zone of their star and outside of it. The habitable zone is the region where conditions allow the existence of liquid water on the surface. Examples of planets in the habitable zone are Kepler 186 EF and Tyui 700d. Others, such as hot Jupiters or scorching super-Earths. Number 44, the best exoplanet candidate for habitability. K218b is often called one of the most promising worlds for habitability studies, but it's not an Earth twin. It's a sub-Neptune, about 2 or 3 times Earth's size, that orbits in the habitable zone of a small red star where temperatures could allow liquid water. Telescopes have found signs of a hydrogen-rich atmosphere with gases like methane and carbon dioxide, which makes it easier to study than many rocky planets. Number 45, some planets have very low density, like cotton candy. Astronomers have found gas giants with astonishingly low density, huge in size but feather-light for their bulk. A standout is WASP 193b, about 1.5 times Jupiter's radius, yet only around 14% of Jupiter's mass. These puffy worlds likely sit very close to their stars, where intense heating bloats their atmospheres and weak gravity can't hold them tight. The result is a planet with cloud-like density, more like cotton candy than rock or even typical gas giants. Number 46, there are planets so dense that they must be almost metallic. There are exoplanets with density so high that they are thought to be almost metallic. An example is HD 149026b with a massive core of heavy elements, much denser than Jupiter. Another case is K2-229b, a super-Earth with a composition similar to that of Mercury, with a large iron core. These extreme densities indicate that some planets form by losing their outer layers or accumulating very heavy materials. Number 47, exoplanets can have extremely short days and years. Some exoplanets have years shorter than an Earth day. They whip around their stars so closely that an orbit takes only hours. At those distances, temperatures soar and tidal forces are fierce, often locking the world into synchronous rotation, one hemisphere in perpetual daylight, the other in endless night. The constant stellar blast tends to circularize their orbits, and the intense illumination drives extreme day-night contrasts in weather and chemistry. Astronomers call many of these worlds ultra-short period planets. Number 48, a 7-hour year on a rocky world. Some tiny rocky exoplanets hug their stars so tightly that they race around in hours, not days. Gliese 367b orbits in about 7.7 hours. No planet in our solar system is that fast. At that distance, the day side is extremely hot, likely tidally locked, and some metals on the surface could even melt or vaporize. These ultra-short period worlds are like superheated embers skimming just above their stars. Number 49, some exoplanets have temperatures above 2,000 Celsius degrees. Some exoplanets orbit so close to their star that they receive immensely strong radiation, which heats their atmospheres to thousands of degrees. For example, the planet K2-229b, a metallic super-Earth, reaches daytime temperatures of over 2,000 Celsius degrees on its side, exposed to the sun. Another example is WASP 76b, a hot Jupiter, whose dayside temperature can exceed 2,000 Celsius degrees, reaching up to 2,500 degrees according to some estimates. Number 50, does it rain liquid iron on some exoplanets? On a few ultra-hot giants, it's plausible, yes. Take WASP 76b, a hot Jupiter so close to its star that the day side bakes above 2,400 Celsius degrees. There, iron doesn't just melt, it vaporizes into gas. Fast winds sweep that iron vapor to the cooler night side, where it condenses again and can fall as molten iron droplets. Astronomers inferred this cycle in 2020 using high-resolution spectroscopy with the Very Large Telescope, which detected signatures of iron moving from the hot limb toward the cooler side. Exactly what you'd expect if metal were evaporating, drifting, and then raining out. Number 51, some planets could have toxic atmospheres. Yes, exoplanets have been identified with atmospheres that would be toxic to terrestrial life. One example is WASP 76b, whose atmosphere contains gaseous iron that condenses and could rain in the form of metal. Another is HD 209458b, where sodium and other gases have been detected in extreme concentrations. Also, in super-Earths such as 55 Cancri E atmospheres with carbon monoxide and lethal compounds are suspected. Number 52, exoplanets can have magnetic fields like invisible shields. In 2014, scientists found the first signs of one around the hot Jupiter HD 209458b. It seems to be about 1/10 as strong as Jupiter's, but still strong enough to make a protective bubble against the star's wind. Magnetic fields can create auroras and produce radio waves. If we pick up those radio signals from far away, we can estimate how fast the planet spins, how strong the stellar wind is, and whether the planet's atmosphere is being stripped. If an exoplanet is so close to their star, they evaporate. Number 53, some exoplanets have monster winds faster than jet aircraft. On WASP 127b, high-altitude currents have been estimated at about 20500 miles per hour. On the ultra-hot Jupiter WASP 76b, day-to-night winds likely reach about 12300 miles per hour. And on HD 189733b, measurements show winds near 5,400 miles per hour, racing from the day side to the night side. These speeds come from extreme heat and strong pressure differences on worlds that sit very close to their stars, turning their atmospheres into global supersonic jet streams. Number 54, super-Earths could be volcanic powerhouses. Some super-Earths may have more intense volcanism than ours. Why? Bigger planets start with more internal heat and hold it longer. They also have more radioactive elements warming the interior. That extra energy can keep the mantle partly molten and drive stronger magma upwellings. If the planet orbits close to its star or a giant neighbor, tidal flexing can add even more heat, fuel for eruptions. Higher gravity may squash mountains, so volcanoes might be broader and lower, but eruptions could be frequent and powerful. Number 55, methane spotted on some exoplanets. Astronomers have found methane in a few exoplanet atmospheres. That's exciting because on Earth, methane can come from life and from geology. A key case is K218b, a possible Hycean world larger than Earth with a hydrogen-rich atmosphere studied by the James Webb Space Telescope. Webb saw signs of methane together with carbon dioxide, hints that the planet might have temperate conditions and interesting chemistry. Methane alone isn't proof of life, but finding it, especially alongside other gases, makes K218b a top target in the search for potentially habitable environments beyond our solar system. Number 56, super-Earths teach us how Earths are made. Studying super-Earths, planets bigger than Earth but smaller than Neptune, helps us see how planets grow. They sit in the middle zone, where rocky cores are still building and thin atmospheres are forming or escaping. By comparing super-Earths to small rocky worlds and big gas giants, astronomers can test which steps make a planet stay rocky like Earth or puff up into a mini Neptune. Number 57, exoplanets can have rings. Some exoplanets seem to have rings like Saturn, but on a mind-blowing scale. The standout candidate is J1407b, about 430 light-years away. In 2007, its star's light dipped in a strange long pattern, best explained by a huge ring system passing in front. Models suggest around 37 rings stretching roughly 180 million kilometers across, hundreds of times wider than Saturn's rings. The companion may be much more massive than Saturn. Estimates go up to about 20 Saturn masses, and the gaps in its rings could be carved by forming moons. Number 58, some exoplanets have an exotic ice at high pressures. Yes, there is scientific evidence that exotic ice forms exist on exoplanets under very high pressures. The exoplanet Gliese 436b is thought to have hot ice in exotic forms, which remains solid despite very high temperatures thanks to the enormous pressure of its interior. Laboratory studies show ice phases such as Ice 7 or new ammonia water hydrations that could exist at pressures of several gigapascals within super-Earth ice sheets. Number 59, a possible moon outside our solar system. Astronomers have reported a candidate exomoon called Kepler 1708b. It seems to be about 6 times Earth's size and may orbit a Jupiter-sized exoplanet, the Kepler 1708b. The hint comes from transit data, tiny extra dips, and timing shifts in the starlight when the planet passes in front of its star. The signals are faint, and scientists need more observations to confirm whether it's truly a moon or just a look-alike signal in the data. Number 60, the radius gap. When astronomers sort exoplanets by size, there's a missing middle between about 1.5 and 2 times Earth radius. Planets that size are rare. Why? Many small puffy planets likely lose their thin gas atmospheres, blown off by starlight or their own heat, and shrink into rocky super-Earths. Bigger planets hang on to their gas and become mini Neptunes. Result 2 common groups, rocky below the gap and gas wrapped above it. Number 61, Kepler 452b is nicknamed Earth's cousin. This nickname comes from the fact that Kepler 452b orbits a star very similar to the Sun and lies within its habitable zone with a period of 385 days. It has a radius 1.6 times that of Earth, suggesting that it could be a super-Earth. Although it is not known for sure if it is rocky, its characteristics make it a striking candidate for Earth's sister worlds. Number 62, Kepler 186 EF was the first Earth-sized habitable zone. Kepler 186 EF is significant because it was the first confirmed exoplanet to be very similar in size to Earth and orbit within its star's habitable zone, making it a strong candidate for having liquid water on its surface. Although its exact mass and atmospheric composition are not known, its modest radius suggests that it may be rocky. It is farther away from its star than most hot planets, which reduces the likelihood that it will get too hot. However, as it is colder and with less light received, its habitability depends a lot on its atmosphere. Number 63, the easiest exoplanets to find are hot Jupiters. They're giant gas worlds that orbit very close to their stars, so they circle quickly and create strong, easy-to-see signals. When they pass in front of the star, they block a big chunk of its light, making transits obvious. And their large mass makes the star wobble noticeably, which we can measure with the radial velocity method. Big, close, and fast hot Jupiters are hard to miss with today's tools. Number 64, exoplanets can orbit stars of any age. Astronomers have found exoplanets around very young stars, around middle-aged stars like the Sun, and even around evolving stars such as subgiants. That spread means planet making is robust. Disks of gas and dust can build worlds in many kinds of systems. Number 65, the idea of exoplanets is ancient. The notion of worlds beyond our solar system isn't new. Epicurus in ancient Greece already imagined countless stars with their own worlds. In the 1500s, Giordano Bruno argued that other stars are suns with planets, some possibly like Earth. Even Isaac Newton in the Principia allowed that other stars could host planets. We lacked the tools to prove it then. But the idea was there long before modern telescopes confirmed exoplanets. Number 66, super-Earths could have more active tectonic plates. Super-Earths could have more active tectonic plates than Earth due to their larger size and gravity, which would favor the planet's internal dynamics. On these worlds, the internal heat generated by gravity could be more intense, which, combined with pressure on the crust, would result in increased tectonic activity. The presence of tectonic plates on super-Earths could be crucial for climate stability and habitability by regulating the carbon cycle and creating a favorable environment for life. Number 67, James Webb is already probing super-Earth atmospheres. NASA's James Webb Space Telescope sees in infrared, which is perfect for catching the faint heat and filtered starlight from small rocky worlds. It's targeting super-Earths like 55 Cancri E and LHS 3844 bi. For 55 Cancri E, Webb's measurements hint at a secondary atmosphere, gas likely replenished from the planet's ultra-hot interior, because its heat and light change in ways best explained by an envelope of gases. By contrast, LHS 3844 bi looks mostly airless, with no clear atmospheric signal so far. Webb can now test whether rocky exoplanets keep atmospheres or lose them by reading their heat glow and spectral fingerprints. Number 68. Stars can literally melt nearby planets into lava worlds. Some exoplanets orbit so close to their suns that the daylight side gets hot enough to melt rock, creating vast oceans of lava. Most are tidally locked, so one hemisphere faces the star non-stop, blazing hot, while the other stays in perpetual night and freezing cold. Rock on the hot side can evaporate into vapor, making a thin mineral atmosphere. Number 69, some may be super-Venus with extreme greenhouse effect. Some exoplanets are so close to their stars that they receive a lot of radiation, which heats their atmosphere and can cause a runaway greenhouse effect where the trapped gases raise the surface temperature even more. In those cases, the atmosphere may be dominated by carbon dioxide or other greenhouse gases, as recently observed in GGI 1214 bi, which is now described as a super-Venus. Number 74, tiny worlds next door. Barnard's star, a cool red dwarf about 6 light-years away, appears to host 4 small rocky planets. They all orbit very close in, whipping around in just a few days, so they're likely hot and airless. Astronomers pick them up by tracking the star's tiny wobble, the radial velocity method. Number 71, the closest known exoplanet is Proxima Centauri b. This exoplanet orbits the red dwarf Proxima Centauri about 4.24 light-years from us. It's roughly Earth-sized and circles in the star's habitable zone. where temperatures could allow liquid water on a rocky surface. Proxima Centauri actually has more than one planet. Besides B, astronomers have found Proxima Di closer in, and there's evidence for a farther companion. Proxima is a flare-active star, so powerful bursts of radiation may challenge the planet's atmosphere and any potential habitability. Number 72, the smallest exoplanet. The smallest exoplanet found so far is Kepler 37b. It's about the size of our moon, which makes it smaller than Mercury, the tiniest planet in our solar system. Kepler 37b was spotted by NASA's Kepler telescope using the transit method, a tiny dip in starlight as it crosses its star. Because it orbits very close to its star, it's likely a rocky, airless world far too hot to keep an atmosphere or liquid water. Think of it as a moon-sized ember circling its sun. Number 73, the biggest exoplanet discovered. The biggest exoplanet known so far is HAT-Pi 67b. It's a gas giant like Jupiter, but nearly twice Jupiter's size and radius. Since Jupiter is a little over 11 times wider than Earth, HAT-Pi 67b comes out to more than 22 Earths across. It orbits very close to its star, so the heat puffs up its atmosphere and makes it extremely low density, huge and light. More like a swollen balloon than a compact world. Number 74, Wispit 2b, a baby Jupiter. Wispit 2b is a young gas giant, about 5 times bigger than Jupiter, circling a distant star. It's only around 5 million years old, so it's still warm and puffy, basically a planet in its childhood. By watching how its size, heat, and orbit change, astronomers get a window into how giant planets form and grow. Number 75, an exoplanet turning into a dust comet. The exoplanet BD plus 054,868 AIB orbits so close to its star that its surface melts into lava. Rock on the day side vaporizes, and that vapor cools into tiny mineral grains that get blown away, forming a dust tail millions of miles long like a rocky comet. The star's heat is eroding the planet. One smoky stream of rock at a time. Number 76, the youngest baby planet we've seen cross its star. The youngest known transiting exoplanet is Tidy 1b. It's a gas giant only about 3 million years old. A newborn in cosmic terms. It orbits a very young star in the Taurus star-forming region, and we spot it because it briefly dims the star's light each time it passes in front. Number 77, the exoplanet that smells like rotten eggs. The hot Jupiter ID 189733bi has signs of hydrogen sulfide in its atmosphere, the same gas that gives rotten eggs their smell. Astronomers spot it by reading the planet's spectral fingerprints as it passes in front of its star. It doesn't mean the planet actually stinks in space, but it's a great clue to what its atmosphere is made of. Number 78, exoplanet Kelt 9b is boiling off into space. Kelt 9b orbits a super hot star so closely that its day side gets hotter than some stars. The heat puffs up a huge hydrogen envelope around the planet, so big it leaks into space like a comet's tail. In other words, Kelt 9b is literally losing mass, its atmosphere being blown off by intense radiation. With an orbit of about a day and a half, it's a dramatic example of how extreme starlight can strip a planet over time. Number 79, Mu-Arae-C is often cited as one of the first hot Neptunes discovered. It has Neptune-like mass, but orbits very close to its sun-like star, completing a lap in about 10 days. Being so near makes it much hotter than Neptune in our solar system. Astronomers found it by measuring the star's tiny wobble. The radial velocity method, which revealed the planet's pull. Number 80, the TRAPPIST-1 star hosts 7 exoplanets, all about the size of Earth. Some are a bit smaller, so they're rocky rather than gas giants. Measurements suggest B, C, E, F, and G have densities consistent with rocky compositions. 3, E, F, and G orbit in the star's habitable zone, where temperatures could allow liquid water under the right conditions. They circle a cool red dwarf in a tight resonant chain, which makes them easier to study as they transit often. TRAPPIST-1 is one of our best natural laboratories for learning how rocky planets form and testing the potential for life beyond the solar system. Number 81, GJ1214b is nicknamed the Water World. GJ1214b was nicknamed the Water World because its physical properties, mass, radius, density, and early models suggested that it could contain a high proportion of water, which would imply oceans or water vapors in its atmosphere. However, more recent research with the James Webb Telescope shows that its atmosphere is thick with aerosols or clouds and that the amount of water might not be as dominant as previously thought. Number 82, Osiris was the first with an atmosphere detected. ID 209458b was observed passing in front of its star, which allowed starlight to pass through its atmosphere. By analyzing the spectrum of this light, Astronomers detected specific elements such as sodium in its atmosphere for the first time, confirming that the atmospheric composition of an exoplanet could be studied. In addition, it was detected that it was losing gas, with a hydrogen envelope escaping into space, further strengthening the evidence for the existence of its atmosphere. Number 83, exoplanet with a week-long year. About 400 light-years away, the giant exoplanet HIP 67522b orbits so tightly that a year lasts 7 days. That close pass seems to agitate its young star, triggering powerful flares that then blast the planet's atmosphere. The intense heating makes the world look bloated and lightweight for its size, and some gas is likely escaping to space. If this continues, the planet could evolve into a smaller, denser world over time, a rare look at how fierce star-planet interactions can reshape a planet's fate. Number 84, the clockwork exoplanet system. Around the star ID 110067, several planets orbit in a neat resonant chain, their periods locked into simple ratios, so each one laps the star in step with its neighbors. The inner planet circles in about 9.11 days, the next in about 13.67 days, roughly 1.5 times longer, and the outer one in about 20.52 days, again 1.5 times the previous. This musical rhythm lets astronomers predict missing planets. Once the pattern is clear, you can look for transit dips where new worlds should appear. Number 85, a planet way out in the deep freeze. T-Way I-7b circles its star at about 52 AIIU, that's 52 times the Earth-Sun distance. For comparison, Neptune is 30 AU, so its year is extremely long, taking many decades, possibly centuries, to complete one orbit. At that distance, the planet is cold and faint, far too far out to give us easy transit signals. So it's the kind of world we're more likely to spot with direct imaging than by watching starlight dips. This distance is much farther than most transiting exoplanets we detect. Number 86, exoplanet hotter than the sun's surface, and the hottest exoplanet. Why so extreme? It orbits incredibly close to its star, so a year lasts only a few hours, and the planet is blasted by intense light and heat. At those temperatures, rock would glow and many materials would vaporize. It's about as far from life-friendly as a world can get, an ultra-scorched planet hugging its star. Number 87, a giant exoplanet around a tiny star. LIKS 3154bi is a Neptune-size or bigger planet circling an ultra-cool dwarf, a star much smaller and lighter than the Sun. What's wild is the size ratio. This planet is huge compared to its star, far larger relative to the star than anything in our solar system. That makes it hard to explain with standard build a core, then add gas models. Number 88, WASP-12b is a hot Jupiter that's being pulled apart by its star. It orbits insanely close. One lap takes about 1.1 Earth days. At that distance, the star's gravity raises powerful tides on the planet, stretching it into an egg-like shape and puffing up its atmosphere. Some of that gas gets pulled off and forms a glowing ring around the star. Measurements also show the planet's orbit is slowly shrinking, which means WASP-12b is spiraling inward. If this keeps up, the star will likely consume the planet in a few million years astronomically soon. Number 89, Ross 128bi is relatively close and rocky. Ross 128bi is considered a promising exoplanet because it combines several favorable characteristics. It has a mass close to that of Earth, suggesting rocky composition. It is relatively close, 11 light-years, which favors future observational studies, and orbits a red dwarf star that is still reducing risks of extreme stellar radiation. Number 90, HD 189733b, glass rain in a hurricane of wind. On the hot Jupiter HD 189733bi, winds roar at about 5,400 miles per hour. In that blast furnace air, tiny droplets of molten glass can form high in the atmosphere. The winds then whip those droplets sideways, so it's more like glass sandblasting than gentle rain. It's one of the most hostile weather scenes we know on any planet. Number 91, the Phoenix planet that shouldn't exist. Tick 365102760bi, nicknamed Phoenix, is a hot Neptune orbiting a red giant star. That star blasts the planet with intense heat and radiation that should have stripped away its air long ago. Yet Phoenix still has a puffy, low-density atmosphere, a survivor against the odds. It circles its star closer than Mercury orbits the Sun, making its endurance even stranger. Findings like this challenge our models of how planets lose or keep their atmospheres around evolving stars. Number 92, an exoplanet is squashed like a rugby ball. WASP 103b orbits its star so closely that the star's gravity stretches the planet. Instead of a neat sphere, it's pulled into a rugby ball shape, a big tidal bulge. This happens when powerful tidal forces tug harder on the side nearest the star than on the far side. With such a tight, fast orbit and intense heat, WASP 103b is a textbook example of gravity reshaping a world. Number 93, exoplanet's days last only about 8 hours. Beta Pictoris b is a giant young exoplanet that spins very fast. One full turn, its day takes only around 8 hours, much quicker than any planet in our solar system. Earth takes 24 hours. Even fast-spinning Jupiter needs about 10. That rapid spin likely gives the planet a bulging equator and could drive powerful winds in its thick atmosphere. It's a supersized world living life on fast forward. Number 94, a planet system riding a hyperfast star. Astronomers have spotted a candidate exoplanet system racing through the galaxy at about 1.2 million miles per hour. The planets seem to be tagging along with a hypervelocity star, likely flung to extreme speed by a past encounter, perhaps with a black hole or a supernova kick. If confirmed, it would be one of the fastest star-planet systems known. Number 95, a planet in a no-go zone of a two-star system. In most double-star systems, planets are either close to one star or far around both. Nu Octantis IB looks odd. It seems to orbit in between, near the primary star, but so close to the companion's path that the spot should be unstable. One idea is that the planet's path is retrograde. It goes the opposite way the stars orbit, which can help stability. It was flagged by the radial velocity wobble of the main star, though some scientists still debate the signal. Number 96, K218b, water world or hydrogen giant. K218b orbits in its star's habitable zone and shows water vapor in its atmosphere, which first made it look ocean-friendly, but it's probably a mini Neptune. Bigger than Earth with a thick hydrogen atmosphere. Under that blanket, pressure and temperature can be extreme, so any surface, if it exists, would be nothing like Earth. In short, K218b is great for studying possible life-friendly chemistry. But it's likely not a blue ocean world, more a hydrogen-wrapped planet with very alien conditions. Number 97, the cold exoplanet on a weird path. 14 Hercules Ci orbits a star about 60 light-years away and seems to follow a strange, unstable-looking orbit. Instead of a neat circle, its path is likely highly stretched and tilted, probably tugged around by another planet in the system. That makes its year irregular and its seasons wild. More like a cosmic roller coaster than a steady loop. Because it's far from its star, the planet stays cold, adding to the mystery of how such a system formed and still holds together. Number 98, the almost next-door exoplanets. The two planets Kepler-36b, a rocky super-Earth, and Kepler-36ci, a puffy mini-Neptune, travel around the same star on very close orbits. At certain times, they pass within less than 5 Earth-Moon distances of each other, an incredibly small gap for two planets. Their near misses make them tug on each other's gravity, so their transits and years shift slightly from pass to pass. Epsilon Eridani b, a near Jupiter next door, number 99, the near Jupiter next door. Epsilon Eridani b is a gas giant only about 10.5 light-years away, pretty close in cosmic terms. It's similar to Jupiter in mass and orbits its star at a comparable distance. So it's a handy Jupiter look-alike outside our solar system. Number 100, exoplanets are everywhere. Astronomers now think almost every star in the Milky Way has at least one planet. Since our galaxy holds over 100 billion stars, that points to hundreds of billions, maybe over 1 trillion exoplanets. In other words, planets aren't rare gems. They're the standard outcome when stars form. And that's all. What exoplanet fact surprised you the most? Leave it in the comments and subscribe. See you soon, your friend Neil.